Okay, let's just dive right in. Everyone, and I mean everyone, is talking about building with AI. It feels like magic is just one little API call away. But what does it really take to go from a cool demo to a real-world application that people can depend on? That's what we're going to break down today. So our guide for this whole journey is the book AI Engineering by Chip Huyen. And as you can see from this quote by Andrei Lopatenko, a director of Search and AI, this isn't just some high-level overview, it's a vital end-to-end guide. We're talking about the practical reality of building systems that actually work at scale. And this really gets to the heart of it. Is building with AI truly as simple as it looks on the surface? We've all seen those jaw-dropping demos. But what happens when you try to build a real product on top of these incredibly powerful models? Well, that gap between the initial wow moment and a production-ready system, it's massive. And to bridge that gap, a whole new discipline has basically popped up, AI engineering, and it's a real shift in thinking. We're moving away from the old world of traditional machine learning, spreadsheets, structured data, and into this new world that's all about prompt engineering and figuring out how to wrangle these huge general-purpose foundation models. It's less about building a model from scratch and way more about skillfully adapting these giants to solve your specific problem. So, here's our blueprint, our map for the real journey of an AI app. We're going to start with the most critical step of all, evaluation. Then we'll get into the core toolkit with RAG. After that, we'll talk about upgrading the model's behavior with fine-tuning, the engineering hurdles of actually shipping to users, and finally, the secret sauce, the self-improving flywheel that comes after launch. All right, first up, the new blueprint. And if you remember one thing from this section, make it this. You have to evaluate first. Before you write a single line of code, before you even think about a prompt, you have got to define what success actually looks like. And look, this is no small thing. In fact, one of the biggest takeaways from the book is that evaluation is often the single hardest challenge in all of AI engineering. And why is that? Well, think about it. With a normal software, a button either works or it doesn't. But with AI, the output is totally open-ended. What makes a good answer? What makes a helpful summary? It's incredibly subjective. So to get a handle on this, you need a system. Step 1. Evaluate every single piece of your application, not just the final output. Test your data retrieval, test the text generation, all of it. Step 2, create a clear guideline that defines what good actually means. Is it about being factually correct? The tone? How short it is? And then step 3, define the actual methods and data you'll use to measure all this. This whole setup becomes your compass for the entire project. Okay, so with our evaluation compass in hand, now we're ready to start building. And the first, and maybe most important tool in our toolkit, is all about giving our AI the right context. We do that using a technique called RAG. RAG, which stands for Retrieval Augmented Generation, is a total game changer. Think of a foundation model as a brilliant engine. It knows a ton about the world, but it doesn't know about your company's latest internal documents or what happened in the news 5 minutes ago. RAG is the system that connects that brilliant engine to a live external knowledge base, kind of like giving it a GPS with real-time traffic data. That's what allows it to generate answers that are actually accurate and up to date. But how does RAG actually find the right information? Well, at its core is a retriever, and it usually works in one of two main ways. The first is term-based retrieval, basically a classic keyword search. It's fast, and it's a really solid baseline. But then you have the really powerful stuff, embedding-based or semantic retrieval. This doesn't just match words, it matches the meaning behind the words. So when you search for transformer architecture, it knows you mean the AI model, not the movie with the giant robots. But here's the thing. Just giving the model the right facts with RAG isn't always enough. Sometimes the problem isn't what the model knows, it's how it behaves. And for that, we need to upgrade its core programming. That's where fine-tuning comes in. So what exactly is fine-tuning? It's the process of taking that big, general-purpose model and continuing its training, but on a much smaller, very specific dataset. If RAG is like giving a car a map, fine-tuning is like taking the base engine and tuning it specifically for a racetrack or for going off-roading. You're changing its fundamental performance to fit a particular task. This brings us to probably one of the most important questions in all of AI engineering. When should you use RAG, and when should you fine-tune? The rule of thumb is actually pretty simple. Use RAG for facts and knowledge, when you need to give it up-to-date info and stop it from making stuff up.
And you use fine-tuning for form and style when you need to teach it a specific behavior like always responding in valid code or adopting your company's brand voice.
Now, in the past, fine-tuning one of these giant models was ridiculously expensive, like rebuilding a whole engine from scratch. But new techniques like LoRa have totally changed the game. You can think of LoRa as adding a small, super efficient turbocharger to the existing engine. It's parameter efficient, which is a fancy way of saying you only have to tweak a tiny fraction of the model. This saves a ton of computing power and lets you create these small, swappable adapters for different tasks, making fine-tuning way more accessible for everyone.
All right, we've defined what success looks like, we've given our model knowledge with RAG, and we've taught it how to behave with fine-tuning. Now comes the final boss, actually shipping this thing to users, efficiently and at scale. When a user sends a request, the model generates its response in two very distinct phases. The first one is called prefill. This is where the model takes the entire input, the user's prompt, plus all the context we pulled in with RAG, and processes it all at once in parallel. This phase is all about raw processing power, which makes it compute-bound. Then comes phase 2, decoding. After it's processed the input, the model generates the output one word or token at a time, one after the other. This part isn't about raw compute. It's all about how fast you can move data in and out of the computer's memory. So this phase is memory-bound. It's the reason you see text appearing word by word in chatbots. And that's the whole puzzle right there. Optimizing for these two very different phases, one that needs tons of parallel compute and one that needs super fast sequential memory access, is the core engineering challenge of serving AI. Balancing the speed, the cost, and the hardware for both of them is what separates a cool demo from a real, scalable product. So we've made it. The app is live, users are using it, but the journey of a real AI application doesn't stop at launch. In fact, this is where the real magic starts. This is what we call the flywheel. So the application's out there. After all that work, is it finally time for the engineers to kick back and relax? Is the job done? Not even close. The real work has just begun. Because this is the ultimate goal. This is the end game of building a great AI application. Launching isn't just about providing a service. It's about starting a data flywheel. Every single user interaction, every bit of feedback, every correction they make, that gives you invaluable proprietary data that nobody else has. You then use that data to further fine-tune and improve your model, which in turn attracts more users, who then give you even more data. This creates this powerful, self-improving loop, a defensible moat that makes your application smarter, better, and harder to compete with over time.